In this section, we review some probability theory, which is quite a tall demand for about half an hour's worth of time, because you'll see that we start this review probably near the end of a typical first semester in probability theory. So we're relying on some of the more advanced topics from that course. So we go through this review to build up again the tools for understanding randomness that we will employ when we are deriving and implementing our Kalman filter solution for estimating a battery state. The reason we're looking at probability is because we're trying to estimate the state of a system where all of our measurements are noisy, and noise is not deterministic by definition. It's random in some sense. We also think about the model of our cell not being perfect, but we don't know in what sense it isn't perfect. If we knew exactly how to fix it, we would. So the model errors are also random in some sense, and we'll be masking that with our description of noisy measurements. So when we encounter something random, we have two options available to us. One is just to say, well, I don't know what the noise value is, so I give up. I can't do any more. And in a deterministic sense, that's right, you can't do any more because you can't solve an equation where you don't have all of the variables in the equation available to you. But in another sense, we could say, well, maybe I don't know exactly what the random noise is right now, but I know some characteristics of the noise, and I'm going to see if I can then carefully describe the characteristics of the noise that I do understand and make a model of my ignorance, if you will. And then if we go down that path, we can use this model of our ignorance to inform what we do on our calculations. And that's exactly what we do. So we need to understand what a random variable is. Now, a random variable is just any random experiment that results in a numeric value. So I can roll a die, and I would get a numeric value between 1 and 6 if it's a normal fair die. I could flip a coin, and the result is a head or a tails. That's not a random variable because it does not result in a numeric value. But if I say I flip a coin, and if it's heads, I assign a variable 0. If it's tails, I assign the variable 1. Then I do have a random variable. So it's just some random thing that happens that results in a numeric value as an outcome. So noise is just by its nature a random variable because it's a voltage error or a current error or something that is numeric in nature. The idea of a random variable is I cannot predict with certainty exactly what the variable would be every time I measure it, but I can characterize the probability of each sample value of this random variable with using a probability density function. And you've seen these before. Probability density function for a single variable might look something like that. This is f sub x of little x, and this is little x. So how I'm using notation here, little x is a value the random variable could take on. Capital X is the name of the random variable. And the subscript is here because if I'm dealing with many random variables, I need to know which PDF I'm talking about. So this is identifying this. F, the subscript, capital X, identifies this as the PDF of random variable capital X. And then what's the likelihood of any particular measurement is given by the height of f of x at some sample point. There are some properties of a single variable probability density function, such as it can't be negative, it has to integrate to 1, things like that you should be very familiar with. We are going to immediately go beyond a single random variable and define a random vector x that would look like this. So random vector x is capital because it's the name of something random, and it's a vector you can see, and it has a component x1, x2, all the way to xn, where x1 through xn are themselves scalar random variables, we can define some vector of numbers. These are not random variables. Notice it's not capital. This vector of numbers has numbers x1, x2, all the way to xn, and this could be a sample out of the random x distribution, where I would just randomly draw all n of these numbers. The random vector x is described by what we call a joint probability density function, or PDF. Joint means that it combines the effects of randomness on every one of the components, describes them all together jointly rather than individually. And we would give it the same kind of notation. F sub x of x is, we read this as the PDF of random variable x evaluated at some point at some vector point x. So if I write this, f sub x evaluated at x0, that means that I am evaluating the PDF fx at first component random variable x1 equals value x1, and random variable x2 equals value x2, etc., all the way down. And you can think of this, although f is not itself a probability, it's a probability density, but you can think of this as kind of loosely the probability that random variable x1 equals value x1, and at the same time random variable x2 equals value x2, and at the same time random variable x3 equals value x3, etc. Now I have to be careful again, because f is not a probability itself, it's a probability density, and if we want to get a probability, really what we have to do is we have to multiply it by the volume that we're considering. So density times volume is just 1. So probability density times volume is probability. So f sub x evaluated at x0 and then multiplied by some dx1, dx2, all the way to dxn, where we think of these as dx being some distances in these different dimensions, is giving us the probability that x is within the hypercube spanned by this x0 point and x0 plus this dx point. So in 3D it would be inside of this cube. There are some properties of a joint PDF, such as it's always positive, it can never be negative at any point. If I integrate over all dimensions, it integrates to 1, which basically says that the probability of something happening is 1, but probability of a specific thing happening, we have to integrate over the region defining whatever that specific thing is. We can define an expected value, which is kind of the balance point of the distribution. In 1D, if I've got a probability density function, the expected value is where basically the probability density times distance away from the balance point added up on one side is the same as on the other side. It's a mass balance. So it's one description of the center of the distribution, but not the only one. We can define a correlation matrix, which is the expected value of x times x transpose. X is a vector, x transpose is a row vector. When I take the product of those, I get a matrix. This is an outer product. So sigma sub x is this correlation matrix that's going to tell us something about the linear relationship between the different components in x, the predictability of one component from another. And then covariance is similar to correlation. If we define x tilde to be x minus x bar is up here, it's the expected value, it's the center in some sense, then the covariance is saying, well, how far away is the random vector away from the most likely or the middle value. So it's a variation, which hence the variance away from some expected point. Then the correlation of x I can apply to x tilde. Correlation of x is x times x transpose, so this is simply equal to expected value of x tilde times x tilde transpose. which is x minus x bar transpose. And one way of thinking about it is to write it out in this integral form, although that's not usually how we end up evaluating it. Covariance is key. If I have some distribution, and let's think about a two-dimensional random vector, and I'm looking at a contour plot of the PDF. There's one contour, there's another contour, there's another contour. Maybe the center point of the PDF is right there. If that's my PDF of something, my best guess for estimating it, what the value is, might simply be the expected value, the center point. But the uncertainty has to do with the covariance, and the covariance has to do with being able to put contours down on this map and say how far away it's likely, how likely is it that if I made a random experiment, how far away would it be from the expected value? How likely is that? That's what the covariance is going to tell us. Covariance talks about uncertainty, talks about error bounds. So when we estimate the state of our battery cell, we're going to use some kind of an expectation to find our best guess of what the state is, but we're going to use covariances to tell us what error bounds are on that estimate. Covariance entries have meaning, so if I look again, it's going to be a square matrix, and if I look along the diagonal of the square matrix, the diagonal elements, the II elements, are equal to the variances of the individual components that comprise the random vector taken by themselves. So the first one is the variance sigma squared of x1. This here is sigma squared xn, all by itself. The other components, if I just take an ij component that's not on the diagonal, that has another meaning. It's going to be the standard deviation, or the square root of the variance of the I component of the random vector multiplied by the standard deviation of the j component of the random vector multiplied by something called the correlation coefficient, rho ij. Rho ij is an indicator of the linear dependence between xi and xj, and it says if I happen to know xi and rho ij, I can come up with an improved prediction of xj from that using some math in the correlation coefficient. So it says if there's any linear dependency at all between different components of a random vector. Rho ij is always between plus and minus 1. So those are just briefly some properties. Hopefully you've seen these all before. If not, you might want to go and pick up a book on probability and go over those concepts in more detail. It might be helpful when we do some derivations later on. There are an infinite variety of probability density functions. There's really no limit as long as you meet all of the criteria such that every point in the function must be non-negative and has to integrate to 1. For example, anything goes as long as the rules are maintained. There are a certain number of probability density functions that come up so often in engineering examples that they're given special names. So maybe you've heard of the uniform distribution, or the Rayleigh distribution, or the log normal distribution, or the Erlang distribution, or in some discrete ones, geometric, hypergeometric, back to continuous, exponential. There's lots of distributions. The only one that matters for us is the Gaussian PDF. A Gaussian PDF in 1D is the standard. It's also called the normal PDF. Same thing. It's a bell shape. It has some mean, x0, and it has some standard deviation, sigma. If I know those two things, actually the mean would usually call x bar, and standard deviation, sigma. If I know those two things, I can completely define the probability density function of the Gaussian. Now, going back to your original course in probability, there's probably a big emphasis placed on learning a lot of different named probability density functions and being able to work with them and apply them to different things. There's a reason we use the Gaussian here, and we'll talk about that reason in a few minutes. But you might remember that the description, the probability density function description, was probably about the messiest for the Gaussian as any other. So fx of x for a 1D is 1 over square root 2 pi sigma times exp of minus a half x minus x bar squared. 1 over 2, there's a sigma here as well that I'm missing. I think it's sigma squared. Might be wrong, but that's roughly what it was. And if you had to do any work with this, it was very challenging to integrate this or do anything analytic with this. And maybe you're at this point and you're saying, oh my gosh, why did it have to be Gaussian? Anything else but Gaussian, please. That was the hardest. But the good news is that the kind of math we need to do with random variables to derive and use the Kalman filter, it turns out the Gaussian is by far the easiest distribution to use. By far the easiest. So this is a good thing for us rather than a bad thing. So we're going to assume ultimately that all noises in our system are Gaussian noises. That means that the uncertainty has a Gaussian PDF. And the state vector itself, because it's driven by some random W process noise, the state vector is therefore a random thing. I don't know it perfectly. And we're going to assume that it's also a Gaussian random vector. And again, this is a good thing. Now in 1D, that formula probably looks familiar. And in 2D, there's all kinds of ways of writing this, well, at least several. And the ways that I usually see in an introductory textbook are really not very helpful. They're good for calculation, but I think in an introductory textbook they assume that you have never seen linear algebra before, so they try to expand the algebra out for you, and it just doesn't add to insight at all. This is the PDF of a multivariable, so a vector Gaussian PDF. F sub x of x is 1 over 2 pi to the power n over 2. So n is the length of the random vector. If n is 1, we have a scalar, and I'd have a square root there, which is exactly what we expect from our scalar random variable case. But then we have this, which is interesting. This says, remember sigma x tilde is a covariance matrix, and it's saying take the determinant of that matrix and then take the square root of the determinant. If this is a scalar, then the covariance matrix is just a one-by-one thing, and we just saw that a covariance matrix on its diagonal, we have variances, so this would simply be the variance. So I'd have the determinant of variance square root. Variance is positive. Determinant of the positive variance is just going to give me the variance. Square root gives me the standard deviation. So this again is exactly the same if I have a one-dimensional thing as I had before, but this is how to properly generalize it to the vector case. Then I have exp minus 1/2. Instead of x minus x bar squared, this is how we do it with vectors. It's x minus x bar transpose times something times x minus x bar, which ends up being x minus x bar squared in the scalar case, but otherwise not. And this here is the inverse of the covariance matrix. So if this was a scalar, it would be the inverse of the variance, or 1 over sigma squared, and that's what I actually ended up writing here as well. So I think these agree. In the case where my random vector x has only one component, but this here is how to generalize when there's more than one component. And again, you might say, oh my gosh, that's even worse. Why would you even say that's the easiest thing to use? Well, hang on, we'll see that. This is some notation we use. This is a short form. We say that random variable x is distributed according to this wavy line means has distribution we're not saying x is equal to, we're saying it comes from a distribution. So x is random, but the distribution itself is a deterministic function. This is something that I can plot. So that's a deterministic function, and that's how we describe x. The script n stands for normal, which is another name for Gaussian. And there are two parameters that are input to a normal distribution. One is x bar, the mean, and the other is the covariance, which shows up in those two different places. If we know those two pieces of data, then we can completely characterize the random variable x. The contours of constant probability, if I do a 2D example, are centered around x bar, and we have contours of constant probability or constant fx are hyperellipsoids. In 2D they're ellipsoids, and the directions of the ellipsoids are governed by the eigenvectors, it turns out, of the covariance matrix and the principal axes. The lengths are governed by the eigenvalues of the covariance matrix. There are some properties of jointly distributed random variables that may or may not be true of any particular random variable. And if they are true, then that tells us additional information that can be helpful in solving problems. The first property we think of is independence. We say if and only if, this means that it goes both ways, if and only if jointly distributed random variables are independent, then the joint probability density function can be split up into a product of individual or marginal probability density functions of the variables, the individual variables. That can be a huge simplification to some math if it is true. Not every random vector can be split up this way because not every random vector comprises independent random variables. If we do have independence, that means that the influence of, that x2 has absolutely no influence on the randomness of x1 because I can split the randomness of x1 off. In fact, no one of the components of the random vector have any influence on any other component or any predictive capability of any of the other components of the random vector. So it's like if I roll a die right now in this table and you simultaneously roll your own fair die wherever you are sitting, the result of the combined experiment of my random result and your random result is a 2-vector, but we would expect that whatever I get as a result would not have any influence whatsoever over what you get as a result. They would not actually cause it in any sense, nor would it predict it in any sense. It's not like on Tuesdays we always roll a 3. And if I rolled a 3, that means maybe it's a Tuesday, so probably you're going to roll a 3 too. That's just not what we expect. So those would be independent experiments. However, if there is, if I have an electrical wire in my circuit over here and another one over here, and there's some big electromagnet making a field over here, then the induced current noise in this wire may be quite similar to the induced current noise in that wire, and those two random vectors, random variables, would not be independent because they come from an underlying source, or there's a relationship, maybe not a completely causative, but at least partially causative relationship from one to the other. So independence is something that can simplify a problem if it's true, but it's not always true. Something else we talk about is whether or not two random vectors or variables are uncorrelated or whether they are correlated. They are uncorrelated if the covariance between the two things, this is the cross covariance, which is the expected value of x1 minus its own mean times x2 minus its own mean, and if it's a vector we would have a transpose in there, is equal to 0. If it's 0, then we that implies that the correlation coefficient rho between those two variables is 0. And it turns out that this means that there's no linear relationship between those two random variables. This is a little different from independence. Correlation or uncorrelation says there's no linear relationship between two random variables of the sort that maybe x2 equals a times x1 plus b plus noise, something like that. So there's some linear causality, but also some uncertainty still. Independence says that there's no relationship whatsoever, linear or nonlinear. So this here is much stronger, and this here is weaker in general. So if I have two things that are independent, then they must also be uncorrelated. If I have two things that are uncorrelated, then they may or may not be independent. We don't know unless we check. One reason that working with Gaussians is nice is that if two jointly normally distributed or Gaussian distributed random variables are uncorrelated, then it turns out that they also happen to be independent. So the weak case implies the strong case, which is unusual. It's something very special. It's not true in general, but it is true for Gaussians. So it turns out usually much easier to show things are uncorrelated than it is to show that they're independent. And if we can show that Gaussians are uncorrelated, then they also are independent, and we can take advantage of some math simplifications, and that's a good thing. Something else you should remember is the concept of a conditional probability density function. And we write it like this, f, because it's a PDF, the subscript of capital X given capital Y tells us that we're talking about a relationship between random vector capital X, it has name capital X, and random vector with name capital Y, talks about the likelihood of X taking on the value little x, given that we know for certain that Y, somehow we have side information, someone's told us this, but random variable Y has taken on the value little y. It turns out that we define the conditional PDF to be the joint PDF, which for two variables we write like this, divided by the marginal PDF of y. So this is like saying the likelihood of x equals x and y equals y divided by likelihood of y equals little y. That's the idea. So this is a normalizing thing to normalize to 1. This marginal probability in the denominator we can calculate from the joint probability by integrating out the variable we don't want. So that's one definition of the marginal. And this conditional PDF is really important to us because we have things that are jointly distributed all over the place, of joint distributions of uncertain process noises, uncertain sensor noises, uncertain states. So we're going to be looking at what is the likelihood of the state taking on specific values given that I've measured certain noisy values. So I've got a noisy sequence of measurements that I've taken, but those help us refine what we think the state might be. So conditional probability is fundamentally absolutely key. That's what the Kalman filter is trying to get at. Using this definition, I can multiply both sides by Fy, and so I have this on one side of the equation. On the other side of the equation I have that multiplied by Fy. So I can expand the joint distribution that way. I could also expand the joint distribution by interchanging the roles of x and y to say that it's equal to f of y given x times f of x. Either expansion, either definition of the conditional will work. Well, since they're both the same, if I set these equal to each other, put that on one side of the equation, and solve by dividing both by Fy, I get this on the other side of the equation, and that relationship is known as Bayes' rule. Bayes' rule relates a prior probability to a posterior probability. So a probability of something what I expected to get before I made a measurement to after I made a measurement. And we'll be seeing that as a key step in our Kalman filter derivation. Well, given a PDF, I can get an expectation. So now I have been given a conditional PDF, so I can create a conditional expectation. And this is critical. This is absolutely key. So this is saying, suppose this was the state of my cell model, and this was a measurement. This is essentially what the Kalman filter wants to find out. Is what is the most likely value of this state given that I've made a measurement? In fact, it's a little bit more complicated than that. This is what we actually end up finding. What's the most likely value of this state at time k given a sequence of measurements from time 0 to time k? We actually have defined yk earlier. Yk in this script sense is equal to little y0 all the way up to little yk. All of the measurements of cell voltage from the beginning of time when I turned the BMS on until the present time right now. The Kalman filter is simply an algorithm to compute that. That is our ultimate objective. If we can compute that, we have a good estimate of this state. If we can do it optimally, so we're taking advantage of all knowledge of noises and things, then we have an optimum state estimate. A couple more things in our whirlwind review of probability. Hopefully you've seen this one before, but it's pretty quick to talk about, even if you haven't. It's called the central limit theorem. It says if I have a random variable y that is computed as the sum of a lot of other random variables, x0, x1, x2, x3, whatever, and if these x variables are independent from each other, and if they're identically distributed, they have the same PDF, and they have finite mean and variance, then y will be approximately normally distributed. This is a strange and incredible result. It's completely unexpected, I think, except that if you've used it before, you've probably gotten so used to it that you just know it's true. This is saying if I take a random variable from a distribution that looks even something like this, like an exponential distribution, and I take a whole bunch of random samples from that distribution and I add the random samples up, I'm going to get something that in the limit looks Gaussian. And how in the world do I get a Gaussian from an exponential? But it's not even saying it for the exponential. It's saying it for anything. It doesn't matter what the distribution is, as long as it has finite mean and variance, which is anything real. And the samples are not kind of chosen with kind of malice. They're just honestly random samples chosen from this distribution. I'm going to get a Gaussian result. And the approximation gets better and better with the number of random variables that I sum together. Now you might think, oh, you probably need 1,000,000 of them. Well, you actually don't. There's a homework assignment I give in my Kalman filter class where I have students just randomly generate a whole bunch of numbers and add them together and then plot histograms, which are approximate PDFs, and you find that after summing together, you really only about maybe 3 or 4 things, this normal looking assumption, just all of us, it already works. If I only sum 3 or 4 things, it already works in practice really well. The central limit theorem says, well, you really have to sum an infinite number of them, but in practice you don't. So why is this valuable? Well, the state of our dynamic system, we've got, xk is going to be for our just assume a scalar, so xk equals a xk minus 1 plus b times the I applied at time k, maybe something like that. And there's noise on this. Well, I'm adding up. When I'm computing x, I start with some initial value, but every time I iterate, I add one more noise sample onto whatever I already had. So our state is integrating or adding up lots and lots of independent random inputs. And so it's reasonable to assume that the distribution of our state tends to be a normal distribution regardless of whatever the distribution is of the uncertainty on the input that I have. And if I've got some kind of a quantization noise, it's certainly not Gaussian, it's uniform, if anything, and so forth. So you could argue very strongly that the noises that come into my system are not Gaussian, and I'd say it doesn't matter as long as there's some independence criteria that's satisfied, then my state is still going to be a Gaussian random vector. This also means if I add two Gaussians together, because they're already at the limit, then I end up with a Gaussian. Now that's not a proof, but it's possible to do a proof. So a sum of Gaussians is Gaussian, a weighted sum of Gaussians is Gaussian. All of this is just related math to the central limit theorem, which is one of the reasons why it's so nice using Gaussians. If I add two uniform random variables together, there's one uniform, there's another uniform, the PDF of the result turns out to have a triangle shape. It's neither one of the things that I started with. In fact, it turns out it's the convolution of the two things that I started with. So if I was working with anything but Gaussians and I added them together, I'd have to figure out what the distribution was of the output, and that's a lot of really hard calculus to do that. But here, because I'm adding up enough things that the central limit theorem holds well enough, we'll just say everything is Gaussian, and it's not a bad assumption. So we are going to make some key assumptions when we derive the Kalman filter. We'll assume that the state is Gaussian. We'll assume that the process noise at the input is Gaussian. We'll assume that the sensor noise at the voltage measurement is Gaussian. We'll also assume that the process noise and sensor noise are unrelated to each other. They're uncorrelated, which means that because they're Gaussian, they're also independent. Even when these assumptions are broken in practice, the Kalman filter turns out to work pretty well. If you know exactly how the assumption is broken, you can sometimes make modifications to the Kalman filter steps to make it work even better, which is one reason we have a whole course on Kalman filtering. But for our case, we won't go into some of those details in this course here. So Kalman filters tend to work really well. They assume everything is Gaussian, and that Gaussian assumption is not a bad assumption. The biggest exception is with highly nonlinear systems. And for these systems, a standard Kalman filter just doesn't work at all. And some of the variations on Kalman filtering that we look at in this chapter, known as the extended Kalman filter and the sigma point Kalman filter, or sometimes it's called the unscented Kalman filter, sometimes those assumptions those filters don't work well either. And in the worst case, for very highly nonlinear systems, when you can't assume Gaussianness anymore, you might have to resort to something called a particle filter. Now, particle filters are great. They can produce the best estimate results, but the computation required is very, very substantially more than anything that we look at here. Again, I do talk about those in the Kalman filter course. If you're interested, you could listen to some of those videos, watch, listen, whatever, to get an idea. But a particle filter is quite tricky. I have seen people employ particle filters to do battery state estimation. I suppose if your requirements are extremely tight, you might be forced to do that. In my experience to date, they have not yet been necessary, but that doesn't mean that they won't be necessary in the future. All right, main point number 6, I've already mentioned that when I add together weighted combinations of Gaussian random variables, I also get a Gaussian random variable. That is a brief whirlwind review of probability theory. All of these things here, I tried to condense everything down into the most important things that we will actually be using in the next lecture segments. So please go back and think about them a little bit, or maybe go forward and see how they're used and then come back and do a second pass if that's of value to you. But these are critical things.